Hello everyone, it's my honor to present our battle research in the conference. This is Tsinghua team from Tsinghua University. Our research topic is a multi-stage approach to detect and isolate multiple leakages in district metering areas in water distribution systems. Our presentation has 4 sections. First, let's see the background. As we all know, there are a lot of negative effects associated with leakages, and a lot of countries have regulations that request water utilities to detect leakages as soon as possible. One of the main problems that we face in leak detection is that we need to detect and isolate them really early. So, the main part of our research is how to reduce the time associated with detecting and isolating the leaks. Operating experience has shown that hydraulic model and district metering areas are useful to control leakage. Focus on the battle theme. The air-town network with hydraulic model and sensors are given in this battle. The challenge for air-town water utility is how to pre-detect special pipe leakages as fast as possible over time. In short, 3 questions need to be solved. First, how to extract the leak-induced signals. Second, how to identify the type of leaks. Third, how to localize the leaks. To address the problems, we developed a novel EILF method for multiple leakages detection. Let's see how the method detects leaks. The method consists of 3 steps. First, estimation of flow and pressure. Second, identification of abrupt and incipient leakages. Third, isolation of pipes with leakages. Let's see more details. As described in the air-town problem statement, the water utility has set up pressure and flow sensors at a few predefined locations in the network. Time series data collected from these sensors are provided. The variations in the pressure and flow data are caused by daily, weekly, and seasonal water usage patterns, leakages, and other uncertain factors. To facilitate the identification of leak-induced data from the time series, flow and pressure caused by the users are estimated by data-driven time series methods. It's assumed that the demand is composed of 10 items, periodic items, and random items. Then, we use empirical mode decomposition to extract the time series items. The EMD can decompose the original signal by subtracting the intrinsic model function successively. The trend items in demand mode can be represented by one of the IMFs. This trend item represents the annual change mode in water consumption in Area C or Area AB. Thus, the estimated value of water consumption in the Area AB can be calculated by equation 2, where QT represents the demand at node I, which is obtained through the hydraulic model. NAB represents the node set of region AB. As shown in the pictures, the blue line is estimated values using our method. The gray line is the residuals between estimated and observed flow. For pressure estimation, the vector autoregressive model is suitable for multivariate time series prediction. The periodic pattern of the original series is firstly removed and serves as the input of the VAR model. Then, we use the residual between the estimated value and the original series to identify the leakages. Because the leakages is an unpredictable event, the residuals would increase when a leak happens. Residual is still a time series with irregular fluctuations. In order to reduce the non-stationary of residual series, first difference and weekly difference are calculated to make the data smooth. The leaks are divided into 2 types, abrupt and incipient. The abrupt leaks are identified through different transformation. 3 sigma SPC limit is used to identify the sudden increase and decrease of the flow curve. Therefore, we can obtain the size, start time and the end time of leaks. There is one more thing to figure out. How does this start time matches the end time? The equality of the variation of the flow is used to match the same leak. A complementary method to address this problem is to sort the pressure nodes residuals. For incipient leakages, a window size-based SVC slope method is employed to identify the incipient increase in flow residuals. For localization, we use the idea of control variates to localize each leakage for area AB. We find two leaks, one with the leak and the other without the leak. Then, making a difference between the observed pressure data at the corresponding time in the 2 weeks. Grid searching is conducted for nodes and emitter coefficient in EPANet simulation, and calculate difference between the simulation pressure results as before. Finally, MSE of two differences is used as evaluation function for this problem. We could find high probability area of leakage with low MSE value. Now, let's see the detection performance of this EILF method. Through difference transformation, the abrupt increase and decrease are easily identified by 3 sigma SVC method. Besides, we sort the pressure nodes residuals, as shown in the second figure. A sudden increase in pressure will lead to an increase in the residual between the current value and its moving average. The variation of the pressure at the neighboring nodes will be higher than more distant nodes. The birth and fix of a certain leakage will cause similar patterns for the neighbor nodes and the distant nodes. By observing the pattern at each start time and end time, a matching could be done. Therefore, 9 abrupt leaks are detected in the battle DMA networks in 2019. For incipient leakages, as shown in the tables, 7 incipient leakages are identified by window size-based SVC slope method. However, the peak of each unfixed incipient leakages is hard to be determined because of the overlap of different incipient leakage. Therefore, an approximate peak time is given for each incipient leakage. For localization, the shade in gray represents the size of the MSE. The pipe with darker color has smaller MSE. Among them, red, orange, yellow, green, and blue indicate the 5 pipes with the smallest MSE. That is, the area with the highest probability of leakage. By using our EILF method, 16 leakages are detected and localized in the battle DMA networks in 2019. Otherwise, 2 unknown leakages are detected and localized in 2018. Now, let's conclude with some highlights of the methods. Applying the EMD and VAR, accurate estimations of flow and pressure under normal conditions are used to extract link-induced values from the monitoring data. Rather than analyzing original pressure and flow signals directly, this study extracts key burst characteristics, reduces the impact of diurnal variations, and provided a better solution for leak detection. Second, weekly difference is calculated to reduce the non-stationary of residual series, which is used for leak detection. We also use the weekly difference idea to design the objective function for localization searching problem. This approach improves the ability to deal with uncertainty. Third, the equality of the variation of the flow residuals and the sorting of pressure nodes are used to match the start time and the end time of an abrupt leakage. Meanwhile, the window size slope variation method is proposed to detect incipient leak start time and size. The EILF method provides an effective multiple overlapping leaks detection framework. Finally, results show that 16 leakages are detected and localized in 2019, which demonstrates the effectiveness of the solution from leak detection and localization in water distribution systems. That's all. Thank you for your attention.